بسم الله الرحمن الرحيم لا حول ولا قوة إلا بالله العلي العظيم حسبنا الله ونعم الوكيل نعم المولى ونعم الوكيل. Good morning, ladies and gentlemen. My name is Hamid Tajurad. I'm the professor at Kansas University of Technology and the director of ARAS, Advanced Robotic and Automated System. In this workshop, we will review observer design, and then optimal Kalman filter is introduced. Then the use of the design for linearized system is given, and it's generalized to extended Kalman filter, EKF. Finally, this EKF is generalized for a global observer for a nonlinear system, and then we conclude with some applications. Just to, before start, since we have a broad range of audience in this workshop, I try to give more basic and introductory stuff, as well as some technical and nonlinear issues. So please obey me with the way that we are considering, and feel free to ask any question during the session or at the end of the session. Now, here, I hope that this workshop will introduce you some questions and some appropriate venue to work on the observers and nonlinear estimation. Nonlinear estimation is a broad range of application in control theory and also in other disciplines, in engineering disciplines. And the picture I chose here in this slide is a very, very interesting effect of prediction of the prey with the eagle, and how fast it can actually hunt its prey. A few words about ARAS. ARAS Research Group is originated in 1997. We are proud of our 22 plus years of brilliant background and contribution and advancement in academic education and research in the field of dynamical system analysis and control, particularly for robotic application. ARAS are well represented by its industrial engineers, researchers, and scientific figures graduated from our group, and numerous industrial and R&D projects being conducted in our group. The main asset of our group is its human resources, developed all their time and effort to advancement of science and technology. One of our main objectives is to use this potential and to extend the educational industrial collaboration at both national and the international level. In order to accomplish that, our mission is to enhance and enrich the quality of our education and research in a dynamical environment. And that's why we are proposing different workshops, webinars, and also many research illustration from our work to a broad general audience. And forgive me if in this particular session, which is mostly on dynamical system design, since we are working on robotic system, many applications in robotic avenue will be basically given and elaborated. What I will be given in this workshop is divided into 5 sections. I intentionally break the workshop into 2 sessions, one session in the morning that I am delivering it right now, and one session in the afternoon. So you have some time to digest the introductory part at the morning session, and then complete maybe some more mathematical issues and the application stuff in the afternoon session. So in the morning session, hopefully I can cover maybe the first 2 issues, the local observer and extended Kalman filter. And in the afternoon session, I will go through the global observer, one particular high gain observer, and some application. Note that this workshop is just an introductory to nonlinear observer. Nonlinear observer can be extended to different venues and different kind of application, and we need more time, maybe 6 credit course, not only 3 credit, 6 credit course to work on the linear estimation and nonlinear estimation. And since it is widely used in different area of application, I suggest you to continue working on this subject in the future. Regarding the local observer, I'll start with very, very simple issues. And forgive me for the technical student and colleagues that this might be a bit somehow less mathematically elaborated. Let me just give a motivation. Maybe this slide is very, very important. Uh, and give the way that I think about the nonlinear observer. Uh, Nonlinear observer comes after nonlinear control. Basically, we have a nonlinear system. We are controlling the system with many different control schemes, either linear control schemes or nonlinear control schemes. And in many of them, we need state feedback. And in state feedback, we need full state information. And this full state information requires a number of expensive measurements. And this is usually not plausible in many applications. So we have to somehow know about the state of a system, but we are limited to measure them. Here, the need of a linear observer comes into the picture. So we need to estimate the states instead of measuring them. Any measurement equipment costs at least $1,000 or something more than that. But the estimation needs a bit of thinking. Of course, it requires a number of requirement to be doing like that. But if we can do that, if the requirement and the assumptions to do that is available, it is much less expensive. But what is an observer, or what is an estimator, mathematically speaking, or in a dynamical system? How we can see an observer? Observer or dynamical is itself a dynamical system that can estimate the state. The difference between this dynamical system and with true dynamical system is this dynamical system has a set of a number of differential equation that is totally executed in a computer or in a processing unit. And since it is basically applied in a digital, we don't have the limitation of actuators, we don't have implementation, and it can be used much in more depth. So these dynamical observers are basically very intuitive and very applicable in many designs. Uh, we start with a linear version of such observer, of course, to gives you the intuition and the basic concept. We need to give you start from a linear designing an observer is very easy since we have a separation theorem. The separation theorem told us that we can design the observer, a dynamical system, separately from designing the controller. And if we make sure that the observer is converging and it is basically stable in the sense of stability that we know in dynamical system, And we know we can design and observe a controller which is also stable and converging in its context. Then the integration of these two together, and in bringing these two together, is becomes stable, and we don't need any more further investigation. This separation theorem is not true in linear system, and that's why we need more analysis and analytical advancement to design the observers. Uh, estimator in context of a nonlinear system is usually a counterpart for a nonlinear state feedback, or a linear or nonlinear state feedback. But starting from this, two people which are very, very celebrated and very highly cited in this area are Leuenberger and Kalman. I will discuss about the biography of Kalman at the end of the session, but these two people start working on the issue to address the request for a nonlinear system control design. But when the theory is advanced and becomes mature enough, said that the state estimator is very, very efficient in many other disciplines, not just in controller design, but in other many other disciplines. Estimation is very, very interesting if we can estimate and predict a dynamical system like weather and meteorological aspect of the environment. It is very good to know at the weekend if we have rain or we have snow or it is sunny then, or maybe we can predict what is going on in the stock market. And it is very good if we know what happened 2 or 3 days later. It is very good to predict if a system is becoming faulty and we have some sensor fault or we have some measurement fault in the system. This is also somehow interesting, and it doesn't really matter to the control design. It is the monitoring of the system, performance evaluation of the system, and prediction. And prediction is always good, and it can brought for you some treasure, basically. And that's why this estimation theory originated from control theory, but has been expanded in a large area and in different disciplines. And as I will show you at the ending session, it is now becoming very, very more applied in the different application. Now start with a very simple linear system. Consider we have just a review on the observer design in linear system. Consider that we have a linear system x dot is equal to ax plus bu, with y is equal to cx, everything linear, everything linear. So the concept of we would like to have a full state observer. Now we can have reduced order, we don't cover that here. You can think about it, the Leuenberger or reduced order observer very easily from what we are extending here. Suppose that we would like to estimate all the state of the system. We have a system like a stock market, we have a system like a meteorological system or weather or whatever, which is of interest of us, or maybe a mechanical system, a robotic system, or any industrial application. It could be in finance, it could be in many area. Now, since we have a estimation here, and then we have maybe also requirement for having the state observer. Now, we would like to produce this estimation through a dynamical model or the dynamical system. A dynamical system a number of differential equation that we are using with some inputs and output. The input is the requirement from the system, some measurement from the system, and the output should be the state that we are basically trying to estimate. So in any type of estimation, model-based, of course, estimation theory that we are using, the observer has two parts. As you see in here, we have part AX plus BU, which we call the motion model or the dynamic model of the system. We use the knowledge, maybe even the knowledge is not very perfect, it is uncertain, but we have some knowledge about the system. So we use the knowledge of the system as the model of the system as the main counterpart or main asset of our estimator. Plus, but this is not enough, because if the model was enough, we could do it just, feed forward without any feedback. And the control people love feedback. I love it very much. So we put another term. We get the feedback from the measurement. We call this part observation model. So the model has two parts. This is the motion model. We call it motion model since many mechanical system, this part gives you some sort of motion to the system. But it is not necessarily motion. It is a dynamical system. That is the model of the system, first part. And here we have a model, very simple model. Both of them are very linear and simple here. We call this part observation model. So as you see, we get in a feedback. You see that, okay, we are estimating the system from the model, but the output of the system, this is really measured. We are not measuring all the states, but we should measure at least one particular, maybe one state or a combination of state in a linear system, which we call at least one measurement. So this gives us a feedback from the true system, and this part gives us the knowledge that we have gained from the model of the system. If we have a very good knowledge of the model of the system, we can put more emphasis on this part. And if we have less knowledge on the model of the system, we will put more emphasis on this part of the system. And the combination of that two, and there is some important particular issue here we call H. H is the observer gain. How much gain we will put on the observation model. How much we should emphasize on the system, and how can we relate them to the states. This is very important. And Luenberger and Kalman has defined how to do that very easily for linear system. So no matter what, which method of nonlinear observer you are using, you will have these two counterparts, the motion model and or maybe the dynamical model and the observer model, the observation model that we put it together. To do that, we should have some detectability or observability issues that we usually learn it in linear control. Basically, the measurement should be assuring enough or informative enough to gain all the state information from the output. So A and C should be detectable technically. It means that the relation between the output and the states are a one-to-one relation. We can get information from the output. And H shall be designed such that we shall design the H in a way that we converge to the true system, maybe at the beginning of this dynamical system. Since it is a dynamical system, it has a rise time, it has some maybe oscillation or anything. But at the end, we converge to the true system state. We will discuss it or we will analyze it through the error dynamics. We use a notation of tilde in a linear system always to define the error of the system, x minus x hat. The hat notation are related to the estimated value. On hat, the true relation on the state is the true value of the state of the system, and tilde one is the error, the difference between x and x hat. And since we have the x hat here, x tilde here, as you see, we can basically analyze the dynamic behavior. Let's see what is the dynamic behavior. We have a system with a dynamical system which is represented with here. We have a dynamical system. Consider that we should apply that in a computer parallel to the real system that will provide us with the estimate of x, and we can analyze the error. The dynamics of the error tilde x tilde dot is equal to x dot minus x hat dot. And if you put these two equation here, you will find a x minus x hat minus h cx minus cx hat. And this can come together at a minus h cx tilde. This is very interesting in linear design, since in state feedback design we have a minus bk. Here we have the dual of that system, a minus hc, and we can even for the unstable system A, we can design H in a way if only the only condition is that A and C is detectable. If this relation is one-to-one, A minus HC, we can design this to be a Horowitz matrix or a stable matrix. All the poles or the eigenvalues are in the left half, open left half plane. So if we do that in here, as you see, we can design this through a pole placement very easily, or some optimal control estimator. We call it LQE or LQG. That is usually being learned in linear system design. I will explain to you about that in a few moments. Now, now considering that we have this issue quite easily, let me just now since we have the motivation in a linear system, now go through the nonlinear system. And start with a nonlinear system and the same concept. Please interrupt me, just raise hand or interrupt me. The people are here to hear your questions and comments. In a nonlinear system, we have the same thing. We're having a model for the system, but a nonlinear model. X dot is equal to f, x, and u. And observation model, and the observation is also nonlinear. So y is equal to hx. This could be a simple single variable model or a multivariable motion model. The more we can measure the system, the better we can get more information about the state. So if we would like to design a full observer, very similar to what we have done in linear system, we put the motion model plus the observation model together with a gain here. But the gain is different. Gain might be at least time varying. It should be different, depending on the dynamics that we are having and the error that we get. But again, higher gains means that we are emphasizing more on the measurement, and lower gains means that we have more focus on the model of the system, and we are more certain about the model of the system. But this balance and this trade-off is given with this gain, and we will discuss about how to design this gain in the few slides. Now, H could be constant or time varying. The term F comes from the model of the system, or we call it motion model of the system. The term H is correcting the term from the observation model, or we have the feedback from that. How to do that? How to do that? In a nonlinear context, we can do that in two ways. One way is the linearization method using the second Lyapunov method for linearization and stability analysis, or using some global model for observer. We cover both of them, not all the details, but we introduce both of them in this workshop. In the linearization method, basically we can design a simple linear observer, a local observer, when we linearize a nonlinear system about equilibrium point. So we have some sort of linearized model for the system, which is true only in a limited area that around the equilibrium point. And we can use that as a local observer, or maybe somehow extend it to extended Kalman filter. And if it is some sort of optimization and required or acquired here to do that, we go to the Kalman filter. Or just forget about the linearization, and we can straight go through the nonlinear model. This nonlinear model could be with uncertainty or without uncertainty. So the both variation we will cover maybe in the afternoon session. I hope that we can go through finalize the part with the ECAF today, this morning session. Now, now that we have this part, let's see about some sort of local observers that we are working. The local observers uh, comes from this here. So we have the full state observer. Let's start analysis about that. So we start with the linearization approach and the local observer in here. The introductory part is finished. Now we can think about how we can analyze the local observer for a system. So we have a nonlinear system, and if you don't mind, I'm using the notation which is given in the book of Khalil at the and also we have some programs produced here. I will provide the programs available to you through the website of the workshop. At the end, that you can have some more training after this workshop. So we have a nonlinear system. We call it 11.1. The main dynamics of the system, the full state observer, as we discussed before here, 11.2, and we would like to analyze the estimation error of the system in this equation with 11.3. Basically the dynamics model of the system or the motion model of the system, and the error that we have in observation model or in the observation that we can get feedback from it. Now consider that we have an equilibrium point x tilde is equal to 0. Why 0? Because we are requesting to have zero error at the end, at least at the states, at the steady state, at the end, as time goes along. So 0 is the point of interest, and we will analyze the dynamical behavior around the equilibrium point for this dynamical system. And we would like to design H such that the equilibrium point is exponentially stable. in terms of nonlinear system, we would like to have some exponentially stable, or at least we asymptotically, but here we can have even a bit more advanced exponentially stable. So we decay, the error will decay exponentially to zero with a small rise time. And then for local solution, of course, this is not always true. Since we are linearizing, this should be true about this error. So we have not much difference between the true system and the estimated system. In a local neighborhood, we can discuss about that. How to analyze this? We will use the linearization method. So we linearize this equation, just take the derivatives and put it at zero at this equilibrium point. You will find the aerodynamics, linearized aerodynamics, from two parts. The linearized part of the motion model and the linearized part of the uh, observation model. Of course, this is not truly nonlinear. This is linear, but this is the way we start, developing the idea here. It was very good if we just leave the linearization and just directly go to the nonlinear part, but this is more advanced, and I need some time for you to think about the concept, and hopefully in the afternoon session we will discuss about that. So we have a nonlinear system, we have linearized it in here, and we can see it is quite clear that since these have some variation, we cannot stabilize the system. We cannot get the exponential stability with a fixed edge for all points. And this is the true limitation of linearization. So what we will do, we need so this is a time varying system. It is quite understood and understandable that H should be also time varying. We don't start with the time varying case. We start with just a fixed variable case here. As we see, consider that H is fixed, and just analyze about the steady state behavior. And we don't go through all the dynamics and the transient response that we have. We go through the steady state equilibrium point. Consider that the steady state of X, we call it with the notation of XSS, it is equal to Rn. To have this, we have a USS. The input of the system is in Rm, and we have an equilibrium point. As we see at the equilibrium point, X dot is equal to zero, and the error is equal to zero for the aerodynamics. And we would like to see, this is in the future, it at times goes to infinity. What will happen? Do we have this convergence or not? The second assumption that is also very limiting is that we are not very far from steady state value. So we know that the error should be equal to zero, and it is not zero usually when we are estimating. If it was always zero, then in a stock market we would be very, very happy if we know how the stock market is growing, or is and sometimes you have some error, and this error costs you a lot of money. So we are not very, very assured about that, and we are not very close to that. But we consider that for a small value, for in a neighborhood with delta 1, around the steady state, either in X or in U state with delta 1 and delta 2, we would like to ensure that the dynamic behavior of the system is converging, it is not diverging. And although we have some error in the estimation, this error is exponentially going to zero. And this should be true for all t. Could we do that? Let's go up and see it again. This can be done with the design of H. And this H should be the observer gain, should be somehow, if we have the detectability, if A and C are detectable, then we can design H such that A minus HC is Horowitz. What does it mean? It means that although your system is nonlinear, linearize it and use a linear observer as before. When A minus HC is Horowitz, it's the same thing that we discussed it in the linear system. Is it true? This is the simplest way. So this means that forget about nonlinear theory for now. You have a system, a nonlinear system. Just linearize it when you're linearizing around a equilibrium point, and use the linear system, and you use a LQE or a pole placement design, and that's final. Of course, this will work, but it is very locally. And it is amazing. It is amazing that although the system could be nonlinear, even this simple design can work. It has a true concept here that I will explain a bit more in detail in future. So in this design, the first observer design that we are designing for a nonlinear system, there is nothing nonlinearity in it. There is only nonlinear analysis. And we are linearizing, getting the linear model of A and C, and then design A minus HC is Horowitz, a pole placement or a LQE, optimal or a simple case like that. And we can have this, we can show that the analysis is nonlinear. We cannot analyze it through a linear system. We cannot use the separation theorem and such so forth because the system is nonlinear, and the analysis will be nonlinear too. And there is a lemma. This is not a very difficult issue. We can show that for sufficiently small norm of the error, a norm of the, if we are close, if delta 1 and delta 2 are small enough, then we can see that the limit of x tilde goes to 0 when t goes to infinity. We have exponential convergence of the error to the 0. How this will work, although this is quite simple, the analysis needs some linear cases. This is some technical, so somehow technical. I will just review on that for the people and my dear colleagues who are here, and they know the basic concept and maybe are looking for some technical details here. The proof is based on Lipschitz condition. We can show that the difference between the true nonlinear system and the linear system, if this could be upper bounded by a Lipschitz constant, we call it L1, and the same thing if the observation model, the true model, the nonlinear model, and the linear part of it, this is also Lipschitz. If this goes to here, then the aerodynamics will be in this form. It has a linear part plus an uncertainty, we call it delta, and this part is particularly stable, and we can show that this is, although there is some discrepancy or difference between the true model and the true system, this part can be shown to be also low upper bounded. It is not much. If we have this L1 and L2, then we can have K1 and K2, two Lipschitz condition on delta. And this, for this constant K1 and K2, we can consider a Lyapunov candidate X transpose PX tilde for the aerodynamic, always is for the aerodynamic. And P is usually defined by the Lyapunov equation, P A minus HC plus A, we call it ATP plus PA is equal to I. Here the closed loop system is A minus HC. ATP plus PA is equal to minus I. You can find the P from a Lyapunov equation and then a matrix Lyapunov equation very easily to put it here, and then we can show that the derivative of the Lyapunov function, the Lyapunov candidate that we are proposing here, is always negative definite through a number of situations. We just put the upper bounds of different terms here, and we can show that V dot is always converging to 0, is a negative definite system if delta 1 and delta 2 is sufficiently small. So this is the first design, the most simplest one. What was the design? Just in few words. We have a nonlinear system, linearize it about the point that you are thinking, and just use a linear observer for that. And it is amazing. Is it working? Yes, it is working because although the model of the system is not very good, since we are using the feedback from observation, it will work. But it is not global. It is very local, and it is somehow fragile. If you go a bit beyond the linearization part of the model, then you cannot have the system. And as you see here, for sufficiently small delta 1 and delta 2 in the analysis, we can approve the approximation or the convergence of the system through the real one. So to do that and to make this happen, to make this Horwitz happening, I add another one in terms of linear part here, which is the LQE design, optimal observer design here. Now we are designing a linear system. So let's design this linear observer quite elegantly. And this quite elegantly is the some sort of, we call it Kalman Busi or optimal LQE design estimator here. So we have a system here. Notice that I put some two small issues here to this system, which are the most important part of the give the reason why linear observer is working. And we are endowed to Kalman regarding this estimation. We have the system, linear system. This could be from linearized from a nonlinear system, of course, as we talked before. But this linear system is not very accurate. And we have a W. We call it the plant uncertainty, the plant noise or model uncertainty. And we can consider that in a statistical framework, not in a deterministic way. We can have a random process or random system. I don't want to go through that much mathematics here, but the concept beyond that is we have a noise here. It is not noise, it is uncertainty. We are not very certain about this model. We are sure that the nonlinear model is different from that. But this difference is put into the term W, which has an upper bound covariance matrix. The covariance matrix, if the covariance matrix is large, it means that we are not certain about the model. The same thing in the measurement. We know that the model for the measurement was HX. It was not CX. And how we can do that? We can see that, okay, the difference between the true observation model and the linearized point is encapsulated with the vector V. We call it measurement noise. This could be somehow because of the model observation model linearization. It could be just because of the real noise that we get from the experiment. So we are measuring Y, and since we are measuring Y, we can have basically some measurement noise as well. So, and these two terms are very important since we are including these observation errors into the picture, into the design picture, and then we design an optimal observer here. And if playing with this V and W, or the Q and R, we call it Q is the covariance matrix of W and R the covariance matrix of V. We have hundreds of papers regarding this. If we increase Q, it means that we have less knowledge about the motion model of the system. So we should uh, lean more on the observation model. We should respect more to the measurement rather than to the motion model. And if we increase V, it means that our measurements are not good. And this will work only if the model of the system is at least good. And the region of attraction, how close we could be about the equilibrium point, are somehow related to the gains that we are using in here. All right, now if we go further and if we have this design, this is a linear design, but you know that this is done for this nonlinear system that we have the linearization here. So this goes and compound with the previous section that we discussed here. So we have a linear quadratic estimator, and as you know, the full state LQE observer comes with a Riccati equation, solving a Riccati equation. Again, the LQ observer has the same, all the two part, the motion model and the observation model as we had before. The gain comes from the some sort of British Petroleum formulation here is PC transpose R. The student who have taken my modern control could recognize what I call the British Petroleum to remember this. And here we have a Riccati equation, which is an extended version of Lyapunov equation. This is a quite algebraic equation. AP plus PA transpose minus PC transpose R transpose R CP plus Q is equal to 0. So we should define first of all, solve this equation. This Riccati equation is nonlinear. Of course, it is solved by a true numerical solution by MATLAB or any other software that you are using. You should give the Q and R here, and one particular case is that R should be basically positive definite, at least since you are using R minus 1 here. And also we should have A and C to be detectable. These two condition holds for the system that we want. So we solve this Riccati equation, and from this Riccati equation we find P. This is we give the Q and R as the given. A, B, and C is equal from the model. We find P here, and then we put P here and find the optimal gain to design this case. This is the most beneficial way to do that. This is called LQE. This is actually, we call it in the literature, Kalman-Bucy filter, or Kalman-Bucy filter is the Kalman filter version in a continuous time domain that we are working here. Anyways, so by doing that, we can minimize. But what will happen really, the concept or the background concept, I don't want to give the proof here. The proof is quite easy, very interesting. I would like to encourage you to read the proof. It has different three type of proof here for in optimal designs. But usually the calculus of variation can be used here, or the perturbation method can be used here. You can look into my book, in the linear book, to see the proof of such a Riccati equation as well. But the concept, the underlying concept here, is that we have a LQE will minimize, what it will minimize is the error. And this error, X tilde transpose X tilde, has both the W and V inside of it. So it has somehow, some part of it is because of the model error or motion model error, and some part of it is about the measurement error. And this will minimize the expected value of this in terms of a non-deterministic approach that can minimize this performance index. And the solution that you got is somehow optimal. Why do I call it optimal? It is not globally optimal because it is dependent on P and R, Q and R. And Q and R are the values that you are giving about the trade-off that you are between the motion model and the observation model, like all observer design that we have. This is stabilizing the estimation aerodynamics to the origin. So we have exponential stability here. And if we would like to, this is a fixed gain. So you once you design the controller, you can use the fixed gain. This fixed gain can be extended to a more realistic and more applicable gain in extended Kalman filter, which we come to in the next one. If we can make this also varying and change the Riccati equation somehow to give us a varying gain. So the gain should be high at the beginning, but maybe less at the end. Or depending on the dynamic behavior that we get, it could be up and down. And this should be somehow interesting to do that, to work on that. Any case, let me give you some examples, refresh your mind. Maybe you can take some water or a cup of tea or coffee to relax, and let me continue. And if there is any question, please don't hesitate to contribute. Here I give a very simple question, a very simple nonlinear system. The nonlinear system is A1 is completely linear, this part, but B times a nonlinear part is like this, and C1, the observation model is also linear. B is also linear, but we have an nonlinear part in the model of the system. So since this is nonlinear, we can take x1 and x2 time varying here. Everything is nonlinear time varying, but we can consider the equilibrium point 0, 0 as the basis for the aerodynamic. And we would like to see if we use that and use the LQE design. Is the output converging? Is the estimator converging to the real state transition or not? Let's check what happened for X. And we can check it through Lyapunov analysis. We don't have any other means to analyze the stability or the convergence of a nonlinear system since it is nonlinear rather than Lyapunov equation. So we have this, and from A, and we can solve ATP plus PA equal to -1. We find the P here. We just give a Lyapunov equation and then analyze what will happen about the derivative of this Lyapunov equation. And if you put the derivative, put the dynamic equation here and put some bounds on them. Here we have x1 power 2 to x sub 2. We can put it like this. This should be somehow smaller than that. And we have a sign here. The sign could be also, since we have two extras, 2 times this could be, and we know that the sign is always between -1 and 1, so it is upper bounded with 1. We put the upper bounds here, and this one here, this one here, and this one here, and then some manipulation here. We see that V dot is smaller than something which is related to the norm of 2 and something which is related to power 1. And is this positive or negative? You see that it has a negative part, but it has a positive part too. But if we make x small enough, if we have x1 smaller than square root of 2, this could be shown to be negative. So it is converging, but it is local. The minimum of v is equal to square root of 2 for x1 smaller than square root of 2. For this part, for this value, we can have a considering a set which v is smaller than that, x1 is smaller than square root of 2, technically speaking, in terms of Lyapunov equation, then inside this set, we see that v dot is negative, and since it is negative, we are converging to 0. So we have a region of convergence here. We have a limited area that we are working, as you see. This limited area, if we are in this limited area, we are working quite well. So we have this is working, but with low region of convergence. And this is usually not good enough for real application like a robotic application. And if you apply it, you will see that sometimes it is working and sometimes it is not working. And this is because of this limitation that we are finding in this analysis that we are doing. So how to improve that? Go a step forward, just one step forward. We have about 15 minutes time, and I hope that we can go through that design as well. Now, design, instead of, now that we have the analysis here, we can design a LQE estimator to this. Let me also design that and implement it on the real computer to see what will happen. When I put Q equal to I and R equal to 1, this is a naive and very simple approach. This means that I don't have any idea about the model, the noise, and I put them all one, together, very equal to each other. And this is not a good design. Although it is working, it will work, even if you just doing this design very naively. So if you put this one to Q and R here, then you can solve the Riccati equation through the MATLAB. It is quite easy. You can use the Riccati command in MATLAB to design that. And when you find P, you can get the estimator error. It is simple values you can get. Since you have two states, you have two values in a vector form, and then simulate the true system together. You know what we are doing usually in MATLAB? If you see my programs that I will provide with you, I have the true system, a dynamical system. I put the observer system again here. We have an augmented state. We have two states for the true system, two states for the observer. We use the ODE or some integration routines to work with that, and we design that for different approaches and for different inputs or states or initial state, and then we plot the true values and the estimated value together. And I will provide the program this for to you to see how it will work. But you see, if the true system was different, we have at the beginning we had about one dimension error in both state 1 and state 2. Quite large error, but you see that we can get with the LQE, we can get to the true values in less than 2 seconds, and this is very, very good. Although that we showed this is quite limited in terms of region of attraction, in real system, as you see, it is approaching quite well to the zero. So the estimation is getting quite well. And these are the true values. This gives you more picture of what is happening. This is the true state, x1, and we didn't know that it was starting from 1. We started from 0, since we didn't know that we haven't any measurement from the x1. As you see, it was a large error here, but it approaches to it quite well. And it is fantastic. It is unbelievable in real pair. And the same thing for x2. It was starting from 1. It has some dynamics here. You see some up and down, and you see that it will converge to the true value quite well. And this is a very, very simple design, just an LQE design for a nonlinear system, but it is working quite well. And you can, of course, if you make it instead of 1, make it larger variance. If you have maybe 10, then this convergence is not giving quite well. So you can work on shop website to see how it is working. Now, I don't recommend for a nonlinear system, although it is working, but I mostly recommend to extend it a bit with extended Kalman filter. The extended Kalman filter has a time-varying gain, and this time-varying gain provides you with more information and more robustness to the real system. So we have the same old linear system as we had before, and we had the basically the aerodynamics here. We had the Taylor series of this as before. We have A and C, the linearized part, and the delta part as we discuss it here. And these details are exactly the same as before, but the only difference is we are not using just A and C to design the controller, LLQE controller. We put another Kalman filter gain. I just give the result. We say that, okay, use a varying gain. Instead of H being quite constant like LQE, make it varying. How varying? This varies with the covariance matrix P that we have. So with the old equation, P and Q are varying. Then, if this is the case, C can vary as well. So instead of making the linearization just for a single operating point, you can have the linearization at any time. So you can have the system at any time. So A and C can be considered time varying. This is the same old trichotic equation, but it has a p dot here. Quite optimal and very, very well here. So we have usual algebraic Riccati equation. We have a differential Riccati equation, and we can work with the system. So we find A and C of the system as time evolves. So if it is quite different from the equilibrium point, we have a different A and C's. We have a different P and we have different gain. And if the variation is large, then the gain is large. If the variation is small, it's becoming to 0, then the gain of the observer becomes. This is really fantastic. This is really fantastic. I don't want to go through all the details of the proof here because of the broad audience that we have, but it is much fantastic in terms of performance. So we have a H, which is variable gain, and this variable gain basically can work with that. Yes, there is a question. Please open kindly the unmute.
Hello, good morning,
Please.
sir. Sir, just I want to
Good
know
morning.
that, like you are saying, A and C both will vary. So, sir, like system poles will also vary in this filter gain H. So, we can say that
Through this replacement way, since this equation is solved exactly at the same time at any instant time. Let's say now we are sampling this system at instantaneous issues. We are getting different gain p here. And with a different gain, p could be at any instant should be changing, and then h is also changing. No, you know that. If H is changing, A minus HC, as you see here, A minus HC, which is the closed loop system, the poles of the system is also changing. But we don't put it intentionally with hand. We consider a dynamic system and a Riccati equation. This Riccati equation will optimally locate the desired poles here to find and this is the main difference of a extended Kalman filter. Of course, it has its own limitation. I don't say this is the end of the world, but it is much better than a simple pole LQE design that we have before.
Okay, sir. Okay. Thank you, sir.
Thank you.
Excuse me, may I ask you a question?
Sure.
I have noticed that there are so many numerical methods to solve Riccati equation since it's a nonlinear equation. So I was wondering now if we have it in a dynamical fashion, isn't it? Does it become much more challenging to solve it?
No, not at all. Very good question, Zara. Like always, you helped
Thank
me just remind me what I didn't tell the student. Uh, but consider that, this equation is exactly like the equation before that we had. The only thing is we have a differential equation here. The only p dot is added to this system. Since the Riccati equation is very important in optimal design, there are many, many very, very optimal algorithm designed to design this system. And since P dot is added here, uh, all not the same number as we do it for algebraic one, but this part can be solved quite easily. Consider that this is not a linear differential equation. This is a nonlinear differential equation, but it has been shown that it has a unique solution. Always it is possible to find the solution if the system is detectable, if A and C is detectable, and it is quite tractable. It has a very tractable solution for that. So don't worry about the finding the solution. I will show you. I will give the result that we can get, and it shows that quite well. And the reason for that is extended Kalman filter is applied almost everywhere. You can't think of that. If you just check Scopus or any search engine on the literature and said EKF application, just EKF application, you becomes books and also so many applications just because of the extended Kalman filter. Just this simple P dot is changing the word quite well. But this is not because of that. What I can say is because of this Q and R. The main important point is that we are adding covariance, we are adding knowledge or encapsulation or somehow uncertainty of the model to the system and also to the noise of the system. And if we give these two quite accurately, and if we can also vary these two, this could be also varying. Since this is a dynamical equation, this could be also varying. And this is very interesting. You can see many papers how to vary Q and R, how to deploy Q and R to have a better optimization here. But the thing is, comparing to the previous simple version that we have only a fixed Riccati equation, here we have some sort of degree of freedom to have dynamic motion, to have different extension being seen in here. We are almost out of time. I just want to complete this part if you don't mind. It might take a bit more, and I would like to have at least 10 minutes at the end to have your contribution to this talk as well. Anyways, we can see that the solution, if the solution P of exists for all t and satisfy the equality, see, it means that this is the solution to U Zahra. It means that although this equation is nonlinear, the solution always exists and it is bounded. You can find the alpha 1 and alpha 2, both positive one. It means that it is always there is a solution here. And also under that sketch, we can show that the error of the system is exponentially stable. I don't go through the detail here of the proof, but this is very interesting and important in terms of the analysis that the extended Kalman filter gives you a tractable solution. Of always giving you a solution. Don't worry about, at the middle of the time, the P just blow up and you don't have any gain. Don't worry about that. It will go quite smoothly, and then you can find a very well solution for that. The only assumption is A and C is detectable. The output measurement should be quite enough, one-to-one enough to estimate the state, and that's the only reason that we have. And we can have very poor model of the system, but if we have good measurement for the system. Anyways, I don't go to the detail. The detail of the proof, I encourage the interested people to see the proof of here and how to see that how V dot is going to 0. I will conclude this part with the same old question that we have, the same example that we have before, to see the difference, how the difference is. We have the same ABC as before with the nonlinear term here. For a linear system, we just use this fixed A and B, but for the extended Kalman filter, we can use a different A and B. A and B, which basically, as you see, we have some X here, so we can use the derivative here, the linearization that we are using here, to bring it into our picture, into our A and B here. At least, of course, you see that here the B is different, varying here. But since in the motion model that we are using, A and B comes into the picture, so therefore we can have an augmented A, which is basically found from, as you see from the derivative of what we have here in terms of the state, 2 times 1 gives you this part, and this part, the sign of the T actually is a time varying gain that is not included in the C matrix. So we have the time varying gain as well, but this B has put some difference in terms of the linearization in the A and B part, in the second row of A. So we have a time varying A. We solve this equation, Riccati equation, with some simple P. We start with I because we don't know how it is going on. Of course, P should be positive definite, so we start with a simple positive definite one, and then go forward. And as you see, we can find this P11 very similarly. We can solve the Riccati equation. We have 5 simultaneous equations. You see, 2 equations for the model, 2 equations for the states observer, and 1 equation for the Riccati equation. We have 5 equations. We put all these 5 equations into a single ODE operation. I will provide you with the MATLAB code for that you can look into that. And then you can run everything all together and find A and P and H varying, and then put A and H varying here. We use the same initial condition, quite large difference between the states and the values, and check the result. As you see, the results are quite well, and it is quite simple. As you see here, the errors are converging to 0. This is the true state of the system. As you see here, is quite after a little transition that you see here, it is very nicely estimating this system state. And this is the convergence of the P values. As you see, start from 1 and 0, but it will change to some value. And since the P is not varying here, from this part, the gain is almost fixed. At the beginning, the gains are much higher. And how we can check the difference between this and the previous one, make the initial condition larger. If you make the difference, error difference 10 times even in the ECOF version, the ECOF is working quite naturally without any problem. But the previous one is not working that well. This is the part, the program that I will provide with you. The main issue in that program is, as you see, the program has two parts. Of course, we are running a ODE equation here. The other part is just plotting that we have here. So the main issue is the ECOF, and the ECOF1 that we are using here, as you see, has three parts. One part is the true state of the system. This is the state estimated system, and this is the parameter for P variable. The ABC is given, the nonlinear part is given, the design parameter part is given, and then the total dynamics is given here. Look at the end part of this. I just explained a bit about that. As I mentioned, we should run everything all together. We have three different dynamic equations. The first dynamic equation, XP, is the true system. XT is the true system. So we have this dynamic system for the true system. Then we have the estimated value for that, the AT that we have here, as you see in here, in this part. We are giving AT here, the Kalman filter model for the system, which is a time varying system. We have A here, and we have PH, this is the estimated of the P here. This is basically the Riccati equation that we have. And this is the H which is given here. Now, if we put the state augmented here, as you see, X true, pH, and 3P. Since our P has three different components, see, we have 3 state here, 2 state here, 2 state here, 7 state. With 7 state, we run the ODE, we find all this through the estimation values, through the initial values that you give here, and you can work with that. So if you want to run with that, try to change the estimation, the initial state here, to find how this will be working. I will conclude my first session here, and I hope this was not too technical and also not too trivial for you, for a general audience. If there is any question, I will be more than happy to answer.
Is W a Gaussian process? The answer.
It should be. It should be. Yes. Reza has another question. Could you open Reza?
Dear professor, can you hear me?
Yes, of course.
I would like to inquire if we have a nonlinear integer program or a nonlinear integer problem or mixed integer problem. How should we design an observer for this problem?
So this is another issue. As I mentioned to you, what we have here is the introductory part of the system. We are considering a continuous time nonlinear system for this. If we have let's say nonlinear digital one, it should be extended to some. This is not that different. But if you have some integer programming, integer programming is also another area. It is not worked with the Kalman filter, because you should have some constraint on the state of the system that should be integer. There are some routines In MATLAB, you can find some routines for optimization. Go and look in the optimization toolbox of the MATLAB instead of the optimal control of MATLAB. And there are some routines that you can work on that. And it is quite different in terms of terminology, the assumption that you require, how this is working and going forward. What is no difference in any idea of observer? You should always have two parts, one part from the model and one part from the measurement or observation. Perfect. It is very perfect with ECOF. As I mentioned to you, since it is linear and time varying, so it comes into the picture of the Riccati equation. You don't need to worry about anything there. And then you have even the separation theorem there as well. It is much better. If it is not nonlinear, it is time varying. The ECOF is working quite well.
Oh, okay. Sounds good.
Perfect.
Hello, thank you for your presentation. I learned a lot. My field is communications, not control, so I'm not sure if my question is accurate. But
don't worry. Just give it to me. I will translate it into control terminology.
thank you a lot. I was thinking about the proof for stability of EKF, and I was wondering you need some Lipschitz conditions around the uh, stationary solution, right? Around the zero error, if I want to say. Or you
Let me
don't need
bring
Lipschitz.
Yeah, let me bring the very good. Your communication, but you are asking control.
Well, I was always interested in control. That's the second field if I want supposed to choose another field. Thank you.
This gives me a bit of time. Thank you for your very good question to give some very short look on the sketch of the proof. This is not the true proof because the true proof is a bit technical, but the sketch of the proof is, first of all, we consider that P is time varying. So since we are using P minus 1s in the V dot, we need to have the inverse of P dot. And with this lemma that we showed before, since P is always positive, has lower bound and upper bound, so it is always invertible. Don't worry about that. But within the proof, regarding your question, you see that we have some linear part, that is going on here, but we have some uncertainty here. The uncertainty is the most difficult part, the thing that we are not, the most difficult in terms of the most challenging, not the most difficult, the most challenging part and the most important part, because we want to use this extended Kalman filter in real communication system, for example, for tracking or for some sort of many issues that you can find in satellite or in different dishes and so forth and so forth. So this part is the main part, which is somehow disturbing or might distribute some constraint on this system. If we use the Riccati equation, the V dot comes to here, as you see, and we can see that the Lipschitz condition that you say, we can see that with some condition, as you mentioned, we can see that this V dot is equal to 3 part of errors: x to the power 2, x to power 3, and x to power 4. If you consider just Lipschitz condition, simple Lipschitz condition, you don't need the power 3 and 4 in here. It would be much more easier. But when you are using a more sophisticated, more complete version of ECOF, so you can have wider range of that. And as you see, you have some positive part here. These are perturbing your stability. These are positive. This is negative. And so you should find a solution for that. You can find a solution for that, which is basically within that solution, the negative definiteness of V is provided. So in short, if I would like to answer your question, yes, if you have the Lipschitz condition, your range of or the region of attraction or the range of working of the Kalman filter is larger. But even if you don't have that, if you have a more general version that I am proofing in the, using the proof, if, of course I didn't proof it myself, but I use the proof that is given in the literature here, you can show, you can see that with some positive constant here, if you can find this positive constant, you can find the region of attraction quite well, and you have exponential stability for the system.
Thank you a lot. Thanks.
Thank you very much
Thanks.
for your good question. Any other question? We have about 4 minute time
Okay. Can
before
I
end of
can I add
session.
something?
Sure.
Okay. Thank you.
Sure.
It's not related to your topic. It's just for our audience. Please feel free to fill in our form for a certificate of participants, and please attend our next session in the afternoon, 6:30 p.m. IRC, Iran Standard Time, and we're looking forward to have you all.
Thank you very much for joining us, and it was really my pleasure to have a broader audience in many different countries and many different nationalities attending us. Please follow our website. We have regularly, we are really dedicated to promote knowledge to a broad number of interested people. And I'm not a very good teacher, but what I know, I will distribute through different webinars and workshops in the future. Thank you very much and goodbye.
Hello. So, but your lectures are not in English in your website. I have seen so many lectures there. So,
Yes, but we are including English lectures as well. You can follow my robotic course now. It is in English. And the future lectures, of course, we are in the basic idea is to promote knowledge in Iran. So we talk in Persian. But I will provide a number of lectures in English. You can follow my robotic course, which could be quite interesting if you have some knowledge about that. Thank you.
thanks.
Thank you for following us.
Thank you.
Excuse me, Professor.
Thank you. Thank you very much and goodbye.
Hello.
Excuse me, Professor.
Sure. Any question?
Hello, dear professor. May I ask a question?
Yes, please.
Thank you for your perfect and excellent presentation. I want to ask that instead of the problem of being low cog, why should we go to use nonlinear observers? Doesn't it increase the computational burden?
Sure. Of course, this is the topic of our next session. We will go through the nonlinear observers. Don't worry, we have that topic for you too. And it has more challenges, more difficulties, but a few benefits, which gives you a wider region of attraction for the system. So please be in our next session, the second part of the webinar that we will talk on, as you see here, we will talk on certain have part and will guide you how to follow the issue in your
Expected value.
Good question, because if we have non-vanishing uncertainty, when you are talking about not the covariance but the variance or the mean value of that, if it is not Gaussian, then the Kalman filter is not working. This area has its own limitation, so it has the assumption that the noise and the uncertainty is Gaussian. But this is not the end of the world. If it is not Gaussian, if we have disturbance, we can add them. If we have non-vanishing disturbances, we can add them to the formulation in terms of if we know them or we know the bound of them, and then we can have some more robust observer design, some other perfection that of course can be followed by the same way that we introduced that in the nonlinear control scheme. We start with the simple one, and then we can add some robustness, some some sort of adaptive version or some other means to do that. But extended Kalman filter is working very good in practice. So don't go to further details if you don't need it. You know, just even if the system is not Gaussian, still the extended Kalman filter has no proof for that. It's not claiming that it's working. But in my practice, it is working quite well. Try it. Just try it. Okay. Thank you very much.
Hello.
And
Thank you
goodbye.
so much.
All right.
Can I ask a question?
We are out of time,
Okay.
but this could be the last question.
Thank you very much.
Yes.
I was wondering what is the difference between the SDRE state-dependent Riccati equation and extended Kalman filter? Which one is better, and why is that? Thanks.
Never ask which one is better. This is, I don't say which one is better. My research, you can see my research. I have a number of very good observer design on state Riccati dependent SDRE and SDREE and RSDRE, the robust case, and so forth and so on. But usually the issue is when you should use them. All of these issues, this is maybe particular interest. I refer you to go to my papers, go to my homepage and papers. I have a number of papers on state-dependent Riccati equation. They are working well if you can put the system into SDE. At the end of the slides that is available also to you on the homepage, and I put it on LinkedIn as well, you can see a number of references that you can follow your question about that.
Thank you very much.
Thank you very much, and goodbye.